If not, then
All right, we'll move on. Okay, cool. So we've seen now a bunch of examples. Great. Oops. We've seen a bunch of examples. Come on, this is off. Oh, it's off. That would be why it's not working. Okay, that's all right. So how do we build sheaf models in general? Well, you know, of course, that's like asking how do I build logic to do any kind of thing. Of course, that's probably NP complete or something. So no, don't do that. But if there are specific kinds of models that you might want to work with, systems of equations of sorts, there's actually standardized sheaves. And I want to show you a few of these. So how do we build these in general? So classic thing that I like to work with are differential equations models. So just for a moment, let's just think about a differential equation. U prime is equal to f of u, or f is some linear or nonlinear function, don't care. So it's an autonomous differential equation. This kind of abomination of the symbol is the space of all possible functions that might fit into here. So this is time, and this is value. This says that I have k derivatives. Of course, I need at least one to solve this differential equation. So you might express this equation by saying, well, I have u prime. If I take a derivative of u, that turns u into u prime. That's this side of the equation. On the other hand, the other side of the equation involves f. F of u is u prime. So this should be a sheaf, right? And then you say, well, wait a moment. Didn't he say partial orders only have one arrow between nodes? Well, that isn't it. And it doesn't even commute because the left side and the right side aren't equal. So that's kind of bad. So how do we fix this? Well, if you're a super abstract mathematician, you say, this is what I need to grow deep side. Yeah, what I said is don't do this, just add some spans. So let's drop in an extra variable, standard trick in differential equations. Say I've got v to kind of separate things out a little bit. Now I've got u that I started with, and also here, two copies. One I take a derivative, the other I apply f. They both better match up. That's what the equation says, right? But these two copies might be different. How to fix that? Add another span. This is kind of the theme. Add these headquarters nodes, add these spans. Drop in another span. Now I put in the identity map. Leaves the function unchanged. Identity map leaves the functions unchanged. Now sections of this diagram, this is actually a sheaf, sections of this sheaf will in fact be solutions to the original problem. The theme is adding in extra spans, just as Donna said, hey, there's a good reason for why this is the case. Now we're heading towards that reason. Is that when you add spans, it allows you to turn a diagram that looks like this, which is not a sheaf, at least not a sheaf on a partial order, into one that is. And so then you can say, great, now if I happen to know my initial conditions, so put in a certain value here, I can go ahead and do the same extending kind of problem, and we'll have some examples of that. Okay, great. Can you do this in general? Yes. In fact, anything that you can describe by a system of equations, of course, there are lots of models that consist of large systems of equations, can be built using a sheaf that's got a post set, partially ordered set with two levels, a bottom level, which are the equations, and the top level, which are the variables. And the stalk over each variable is the set of possible values that variable might take. Seems reasonable enough. The stalk over the equations is actually these spans. It's a subset of the categorical product, subset of what the different variables involved could be. And that subset ends up aligning with the actual values. And the restrictions end up being all projections. Now, this theorem is constructive. It's a little awkward. So all the constructions that I'm going to show are a little simpler. If you're interested in the reference, here's the reference. Actually, it's in a book chapter, which is expensive. So here's the archive link. It's the same thing. Also in the reading materials, so you don't need to worry when I flip to the slide. So let me show you how this works. I had a student who was actually an economist who was really interested in macroeconomics. And so was interested in this very, very simple description of a national economy. Actually, if you squint your eyes and then think about dynamical systems, you will realize this is a predator-prey system. I don't know what that means anyway. Yeah, but you can see, all right, fine, let's follow the recipe. I've got some equations, two equations. two variables, two equations, two unknowns, kind of diagrammed out like that. And we do the same trick. We say, well, actually, there's a few equations we haven't seen, because we need to tell that u prime means derivative of u and v prime means derivative of v. Okay, so let's put those variables in and put in two more equations. And now this is a sheaf whose sections will in fact solve this differential equation. And you can go off and play around with this. The reason why this was actually relevant to this particular economics student is this was his starting point, and then he went and built a variety of these and networked them together to make a model of a world economy without too much effort. And then was able to notice that in certain cases you could get chaotic behavior. That's a little alarming. Here's the, if you want the actual stocks, the function spaces, no problems. Now, additionally, you can handle Bayesian networks, cause-effect structures, do calculus, all of that can be captured. So here's a simple example of a Bayesian network. We've got the season. The season somehow probabilistically determines the temperature, and the temperature kind of probabilistically determines what your clothing choice will be. How does it do so? By way of conditional probabilities. Given the season, you can determine the temperature. Given the temperature, what's the probability of your clothing? All right, fair enough. You'll notice there's differences in data types here. Season is categorical, perhaps. Temperatures, numeric. Clothing, well, last I checked, is categorical. Well, I guess maybe with one exception, that being the length of your tie. I'm not wearing a tie. All right, anyway, causal networks are basically Bayes networks that you do surgery on. So you say, I'm going to do temperature equals 20 degrees Celsius, i.e. turn on the AC, air conditioning. And now you no longer care about the season. And now you've got clothing choice dependent entirely on this do action. Okay, cool. Can we turn this into a sheaf? Well, isn't all of this under the hood a system of equations? Of course. So let's do it. So let's try to write out some equations. I've got the probabilities associated, joint probabilities associated to each of these pairs of variables. I know the conditional probabilities and the marginals. Great, this is definition of conditional probability. All right, looks like that. But you'll notice we're missing stuff, like what's the probability of clothing alone? Can't really isolate that. So we need some more equations to describe what's going on. And if you look at how BayesNet software works, they're nice tools for doing this. They're actually kind of elaborate because they end up realizing, oh, from that BayesNet, I need a lot more equations. All right, fine. Here's a lot more equations that then marginalize out each of the different variables that are involved. So just to take one of them, they're all the same form. I have the joint probability between clothing and temperature. If I marginalize out the clothing, I just get the temperature, and so on. Of which, there's a bunch of these, all right? But actually it turns out, we're missing some, and IIT people will know there's a simplicial complex involved. Oh yeah, I need the three-way marginals in there too, and so on. Yeah, I see some shaking heads there, yeah. All right, but for this particular case here, that's everyone, because I only have 3 variables. If I put 4 variables, I'd need a bigger slide. Okay, great, this is now everything. So if I want to sheafify, the things are already getting kind of busy with the names, so I'm going to summarize the names. X is here. So there's 2 conditional equations, 9 marginal equations, and basically we run the same recipe that the theorem says we do. We need a bunch of different kinds of restriction maps. I don't want to write them all out because that would be kind of busy on the slide. So just notice you can actually figure out what they are based on the types. If I'm going from a joint with multiple variables to a smaller number of variables, that has to be a marginalization. No way around it. Go the other way, add more variables, that has to be a condition. Conditional, no way around that. So just by looking at the types, we actually know what the functions are. So if you try to code this up in PySheaf, which we did not do, but you could, then you would have to keep track of that, and it's not hard. Okay, so let's write it out as partial order. Here's all the marginals. They're all there. And all right, let's drop in those 2 conditionals. Actually, I need a few more identity maps. Now everything is good. So the global sections of this sheaf, i.e. if I were to drop in probability distributions for everything, such that consistency is maintained across the board, those are in fact solutions to the BayesNet. Okay. Can I do the do calculus? Of course I can do the do calculus. What do? I want to do a do action on x2. How do I do that? Well, I'm going to do surgery on the BaseNet. Cross out this arrow, which I didn't cross out so you can see it. I just made it red. That involves eliminating that arrow, that restriction map. And additionally, the do calculus says when I'm doing x2 is equal to something, I actually make x2 equal to something. Where is x2 in this diagram? Well, it's in a whole bunch of places, but x2 on its own is only in that top spot. So we end up with an assignment that's sitting right here with a value right there, and then we optimize the rest. So any global section that takes on the value that we wanted given the do action at the top will in fact be what the do calculus says you should do. So short answer, causal modeling is part of sheaf theory. So, and that of course is part of category theory. Cool. Now, you might ask, in fact, I'm gonna, you know what, actually, I'm looking at the time, and you might ask, just sort of summarize this briefly. You might ask, if I'm solving a differential equation, what's the right discretization? Can I solve a function that involves derivatives on the computer? Like take a limit as x goes to 0 on the computer? Can I do that? Sure, right? Approximately? Can I do it exactly? Actually, yes, there's something called automatic differentiation. If you're a math nerd, it's awesome. It actually is why machine learning is happening, because it actually is the computational speed up that made all of those gradient descent things work. All right, but that's beside the point. Okay, short answer. How do I choose the right discretization if I'm not going to do that? And generally speaking, the way you do this is you say, well, I got a function, and I'm going to take a bunch of samples, a bunch of values. Okay, that's one way to do it. But there's another way to discretize. The other way to discretize is to say, I'm going to make my function a linear combination of a bunch of known functions. This is where the automatic differentiation lets it on that side. This is actually the better way, if you can make it work. Okay, how do I solve a differential equation? Well, I take a derivative that drops the smoothness and changes the function. Of course, you'd say, hey, all right, fine, I could do the two discretizations, sample it or break it up. Is it commutative? No, not usually. Why? Because we didn't actually take a limit as h goes to 0 when solving our derivative on this side. And probably not over here either, unless we're really super careful about coming up with the right basis. Automatic differentiation is about finding the right basis. And so the point is, you can see right away, failure of commutativity actually has numerical effects. And so what I can say in general is, if you fail to make a commutative diagram, there's probably an implication, which is why our sheaves need to have commutative diagrams. Now, you can go ahead and build these kind of approximations. And so we're ready to flip over and do some computational stuff. More questions? I will take more questions. Yeah. Pass the mic.
So the do calculus section is very relevant for IIT. And so the question is there potential maybe to speed things up computationally there? Because you still have to iterate though, right? To optimize.
Yes, you do. However, the point is, okay, so here's the problem. The problem is that for IIT, I don't actually know what the computations are. So you guys will have to educate me. Just really simple there.
Can you briefly explain the computation activity again?
Yes. Yes. Okay. So if I take a function and I grab some values at some points of that function. So imagine I've got like sine of x. And I evaluate sine of x at x equals 0, at x equals 0.1, x equals 0.2, and so on. if I take that's what lives at that top Rn. What's here is I took the derivative of sine of x. What's the derivative of sine of x? Yeah, some of you guys know cosine, right? Great, good. Okay, and if I sample that cosine, that's what lives here. Is there a nice matrix that will always work, because differentiation is linear, that will always take me from that vector of sine of x values to the cosine of x values? And the point is that actually you can force it to work for sine and cosine. But then if I swap out for a different function, it won't work. It'll be slightly off. There'll be some error. That's why there's a failure of commutativity here. If it worked perfectly, then calculus would not be needed. The failure of commutativity here is actually an expression that calculus is necessary to talk about derivatives. The other side of this, it says, let me try to write a function as a sum of a bunch of functions, maybe a sum of sines and cosines. Fourier series. Can I take derivatives in Fourier series land? Yeah. Actually, that one works a little better. Sometimes, if you're smart about choosing your basis, i.e. Fourier series, then you can do this guy exactly. If you're not so smart about it, you pick splines or something, then you end up with error. Does that answer your question? More or less. Any others? All right. You got a question? Yes, about the do calculus. Yeah.
So here you're fixing x2,
I'm
right?
fixing x2.
And then that fixes the m of x2
That's right.
at the top,
Yep.
but not at the bottom.
Not at the bottom. Why? Because this arrow is an identity map. So if you minimize consistency radius, well, that value there will end up over here necessarily. Because I'm asking to minimize all the prediction residuals. So that value ends up over here, which then actually gets passed along that particular conditional, just as the do calculus says it ought to do.
Okay, so it kind of propagates.
It
through
propagates through the rest of the network.
Extension thing.
That's
okay. And also xy, x1.
Yep.
Is now conditionally kind of disconnected. So the red one is removed, right?
That's right. The red one is removed.
And then that has also some kind of propagation.
That also has some kind of propagating effect as well. That's right. Because you can run up into situations where, I mean, this case here, we've satisfied the backdoor condition. Normally, if I don't satisfy the backdoor condition, then popping off one of these guys may still cause x1 to affect others. Remember, the whole point of Judea-Pearl's do calculus is I want to be able to manipulate this whole thing. I want to do it in a nice computational way. So I'm looking for instances where the backdoor condition or front door conditions or whatnot are satisfied. What if they're not? You're not completely out of luck. This methodology will still let you compute a do action.
Okay, I need to probably think about.
Yeah, this is like cutting edge stuff.
Yeah, I've never seen this, so that's why.
Actually, I will say it this way. You guys saw this first here.
Oh,
this is really cutting edge.
Could be wrong then. For the review.
Fair.
Like my periodic table.
All right, cool. Let's flip up to the next slide deck here and give you the mic.